Okay, well, I'm looking at 5 old exams here. Nobody has questions? Yes, sir.
All right, I found it.
Tell me the year for...
The file is exam 2. It didn't really have the date or anything.
Yeah, but at the top of the exam, doesn't it say like...
Oh, yes. Fall 2011.
Aha. Fall 2011.
And then problem 1, it's a convolution problem, and when I went to go set it up,
Yeah.
I was going to move my A to T. I wasn't sure, should I do it at intervals of 10 or 5? Yeah, I don't know what it's like. T minus 5 or T minus 10, you know what I mean? That'll like shift it across X of T.
Right. Okay, well...
I might have explained that horribly.
No, I think I know what you're saying. I mean, so what you're saying is that essentially the... You know, X of T is that decaying exponential, right?
Yes.
Okay, and it's sort of... Looks like it's done mostly decaying by 5 seconds. And then H of T is a square pulse with area 20 seconds. Is that right?
Yeah.
So first of all, I don't think I'm going to put convolution on this exam because we basically just started it and we have not yet gotten through the convolution recitation. So I would not... Well, you still need to know it. Is that bad? I can put it on there.
Yeah, that's pretty much what I did.
You guys want convolution?
Less word, the better. We already got devastated by a hurricane.
I didn't say that. Yeah.
I would say this. I would say if we'd had a Mondays class, I would definitely have put it on there. But not having had Monday's class, I'm going to feel a little bit anxious about putting a nasty I could push the exam until Monday, but then I would have to write the exam over the weekend, and I have no desire to do that. I had other things to do this weekend. Okay, I'll answer your question. So basically, you've got X of T, which looks like this, and you've got H of T, which looks like, we said 20 seconds? Okay, so the idea is that, well, first of all, we accept that we can flip either one of them, right? So which one's easier to flip?
You can flip either one.
Either one. Remember, because convolution is, whatchamacallit?
Commutative.
Thank you, commutative. So you can flip either one. So which one's easier to flip? Square wave, because it looks exactly the same once you flip it, right?
It would be harder to find our interval when we convolve X of T.
Not really.
So it's hard to notice if it died at 5 or 10.
Okay, so let's discuss that. So there's this whole lecture that I do on convolution, which we haven't done yet, and I don't want to burn your entire review on this, but let's invest 5 minutes and at least just kind of get through it. So what I'm going to do is I'm going to take X of T, and now here's my H of T, and I'm going to flip my H of T. Okay, so now everything is, and I'm converting my axis from T to tau. Okay, so X of T is, what is it, e to the minus T? Well, I guess it's e to the minus tau now. All right, what's this function equal to?
H of minus 10.
Right, it's just 1, right? Just the constant, right? And this is the most critical point. What is the value of this lead point? If you just flip it, it's 0. And then if you do t minus tau, it shifts forward by t units. So this will always be at t. Right? So again, just to go through the steps. You start with this. That's h of t. You convert it to h of tau, it's the same thing. It's just t becomes tau. So this is your h of tau. If you then do h of minus tau, I'll pretend that's a square. Okay. So this becomes 0 and this becomes minus 20. That's h of minus tau. So all that was the flip. Yes, sir?
If it was already on the left, but we need to flip to the right, it'll be h of positive.
Sorry, if what now?
If it's already on the left,
Yeah, then it would flip to the right. That's exactly right.
so it'd be h of tau.
No. So you're saying, like, what if your function was like this? minus 20 to 0?
Yeah.
Yeah, then when you flip it, it would go from 0 to 20, but that would still be on the tau axis.
Does it work with certain functions?
Say again?
It works with every function.
Yeah, absolutely. Now, this is h of tau. Now I need to shift it by t units. So remember, when we did t minus tau, did that shift it to the left or right?
To the right.
Let's shift it to the right. By how many units? T. So if I make this t minus tau, I got to shift this to the right by t units. So all I do is I add t to that. That shifts it to the right by t units.
That would be 20.
And what happens to this unit? What happens to this? I add t to it. Which makes sense, right? This point always has to be 20 units behind this point. Wow, that was cool. I never get that.
That was like the missing ingredient.
That was the missing ingredient. Now, once you've drawn this picture, that's the hard part. Okay, once you've got this picture, you're good to go. Because now look what you do. Now you come along, draw your h of t minus tau. So I draw my h of t minus tau. So this is t minus 20. What's my limit of integration?
T minus 20 minus t.
No, because remember, I'm multiplying these two functions together.
0 to t.
Right, and I'm only integrating where there's non-zero product. So for tau less than 0, this function is going to be 0, so their product is 0. And for tau greater than t, this function is 0, so there's nothing to, when you multiply them, there's nothing to integrate. So the only time when there's non-zero stuff to integrate is from t to 0.
Is it also fair to say whenever they overlap? 'Cause I guess that was kind of my strategy. Is like whenever they overlap, those are going to be my limits of integration.
Right, exactly right. So we're going to integrate from 0 to t, e to the minus tau, that's your x of tau, times h of t minus tau, d tau. Now I'm not done. Let's sit tight for a second. So that's going to be my y of t. Is that going to apply for all values of t? No. What values of t will this integral apply for? Like, okay, so let's say t equals 1. Okay, will that integral work? Yeah. Right, if this is 1 and this is negative 19, I'd be integrating from 0 to 1. Yes, sir?
Oh, I'm sorry, the lower bound of integration of 0 doesn't matter. If t, I'm sorry.
It does matter. Go ahead.
No, it does, apparently. I just realized that.
Okay. Okay. Okay, so what about if t equaled 50? Would this integral still work? What would my okay, so suppose t equaled 50. What would happen?
T minus 20, 50.
Okay, so we can agree that I can try different values of t. Right? So if t is equal to 1, I can use that integral. If t is equal to 2, I can use that integral. But
Is 10 and not really gonna have much in the top part.
what right. So in other words, now what if I keep increasing t so that now they look like this? This is still t minus 20, and this is still t, but I'm using a bigger value of t. Like now let's say t equals 25. I mean, can I do this?
If it's 25, isn't it be all 0?
No. I can take this function and multiply by this
You
function.
gotta change your integral that you got there, though.
I've got to change my limits of integration. So if the picture looks like this, what's my limits of integration?
T to t minus 20.
T minus 20 to t. And then it's the same integral, e to the minus tau times 1 d tau. So question, what values of t does this integral apply for?
When they overlap.
T greater than, go ahead, guide.
When t minus 20 is greater than 0.
Exactly, when t minus 20 is bigger than 0. When does that occur? When t minus 20 is bigger than 0.
When t is greater than 0.
That's the same as t greater than 20. So this will be y of t when t is greater than 20. What about this integral? When does this integral apply? Right. This will apply not just less than, this will be y of t when t is less than 20. Always, what about if t is negative 1? What will this picture look like if t is negative 1? Right. If t is equal to negative 1, then I've got this picture. What's my integral there? 0. Okay. So that top integral can't always be for t greater less than 20. It's also got to be for t greater than. Right. You need t to at least be bigger than greater than 0 in order for this integral to apply. There you go. And what about for t less than 0? What's my answer? What's y of t for t less than 0? Yeah, exactly. If t is less than 0, their overlap is 0. So in actuality, my answer, the answer to the question, what is y of t, is defined by 3 integrals, right? So if this is my y of t, when t is negative, I get 0. When t is between 0 and 20, I get that integral, which I'm guessing is going to look a little bit like this. And then when I do this, and then when t is bigger than 20, I'm going to get the middle equation, which I'm guessing is going to look like that. The end.
When's it 0 after 20? You get 25?
Yeah, well, it never truly gets to 0, but yeah, roughly 25. Yes, sir.
Can we do springs?
Are we done?
So there's going to be
Yes, we can, but let's just make sure that
there's going to be 3 y of t's in our final answer of convolution.
exactly.
You got to account for all conditions.
And that's what makes convolution complicated, right? It's like and again, I don't want to bog down this lecture with this because that's sort of why we're going to do recitation this week. But the essential idea is that once you take your h of t and flip it and slide it, then you have to kind of mash the two pictures up and think about how the two functions overlap as a function of t. Sometimes there's no overlap. Sometimes there's different overlap depending on like what the shapes of the two functions are. So you have to be mindful of that.
So is that why you think of the bottom one as shifting with time?
Yes. Yes.
And that's, yeah, because I think you also said in your book you kind of have to play like a guess and check game to figure out.
Yeah.
So you're just taking different values of t and then finding out, okay, where do they overlap?
Yeah. Yeah, absolutely. Yes.
Can we do spring 2012, the first problem?
Yeah. Do you have something you want to add to this?
So through the option of integrating between like t minus 20 and t or actual numbered values, should we use? Is it preferable to use one or the other?
Oh no, you have to use the t. It won't work if you put number. If you put numbered values, then you will only be solving it for that specific value of t.
Is that loss of generality? Or?
Yes, it's loss of generality. So we have a request for spring 2012 problem 1.
Yes, please.
Okay, let me read this. So spring 2012 problem 1, solve for x of omega the Fourier transform of x of t shown below. For partial credit, you should at least set up the integral even if you can't solve it all the way through. Oh, I love this problem. Spring 2012, first problem. And I'm asking you to get a Fourier transform. Now here's why I like this problem. There's an easy way. There is a hard way. Okay? Which would you like to do first? The hard way? Just do the easy way. You save yourself like an hour. That's the whole point, right? So a lot of these problems are structured that, like, so sometimes people complain, the exam was too long. And my answer is almost always, it's too long because you did the long hard way for each problem. There was a shortcut, you know. And so in essence, part of what I'm testing is, do you know this stuff well enough to understand the shortcut? So let me just see if I can draw this properly. So -1, -4, 4, 6. So I'm giving you this function. So this is x of t. This is, what do we say?
It's going to be derivative.
Minus 1, minus 4. Exactly. Minus 1, minus 4, 4, and 6. Okay? So all I want is to get the Fourier transform. Okay. So let's start with the hard way. So at the very least, I'll set it up. I may not do the whole integral the whole way through. But the hard way is, first, find the equation of that line, and then apply the definition of the Fourier transform. So we know that the Fourier transform is integral over all time, which in our case, all time is going to be from minus 4 to 4, right? Because everywhere else it's 0. And then it's going to be
Minus 1 to 4.
x of t, e to, oh yeah, sorry, minus 1 to 4. Thank you. E to the minus j omega t dt. So if I can just figure out the definition of x of t on that limit, then I'm good to go. So let's see. What is the equation of x of t?
Negative 3 plus t.
I have a vote for negative 3 plus t.
Your y-axis should be at negative 4. You got it negative 1 to 6. It should be negative 4 and negative 1 to 4.
No, this is negative 1, negative 4. No, that's right. And this is 4 comma 6. Are we not looking at the same?
The y value should be negative 4.
Yeah,
The x should be negative 1.
Yeah.
Oh, I beg your pardon. You're absolutely right. This is minus 4. No wonder I got the integral wrong. There we go. Is that better?
Yeah.
Yeah. You're absolutely correct. So it's a line. And part of the reason I put this problem on this exam is last semester I got really upset that nobody could derive the equation of a line. In fact, we had a quiz where I drew a line and I said, get the equation of this line. And I told the students that we were going to have this quiz, and not everybody got a 5 out of 5 on it. All right? So, you know, as with many things, getting the equation of the line should not be the hard part of this problem. Okay? If this takes you more than 30 seconds, you know, you got to figure out what's up. So, equation of the line, first thing you need is a slope. So slope is rise over run. So it looks like the rise is a total of 10 units. The run is a total of 5 units. So this line has a slope of 2, right? So it's 2t. Now I need a y-intercept. I don't really feel like eyeballing the y-intercept. So instead what I'm going to do is I'm going to plug in one of these xy pairs and solve for b. So I know it's going to be y equals 2t plus an unknown b. So I can sub in either point. So why don't I sub in this point? So this point is going to be, the y value is 6. So 6 equals 2, bless you, times 4 plus b. So b equals negative 2. Okay. And if I wanted to use the other point, I could have done this point and I would have gotten the same b. All right, so now I know the equation of my line, 2t minus 2. So my integral is now minus 1 to 4, 2t minus 2, e to the minus j omega t dt. Okay, and now go make yourself miserable integrating that. All right. In fact, I've even given you the table of integrals for t e to the at. So if you wanted to do it, you would break it up into 2 integrals. One would be 2t e to the minus j omega t. And then you would use the table of integral that I gave you to integrate that. And then you'd have 2 e to the j omega t, which is a little easier to integrate. And then you'd fill up about 3 pages of calculus coming up with the right answer.
Now, should the minus 2 be an impulse?
Nope, it's just minus 2.
No, in the frequency domain, because we're adding a constant.
Ooh. Ooh. Fun question. Yes, that will have the effect of putting an impulse at omega equals 0.
So that can't be A0.
That's nice. Do you guys see that point that we just made? Right? If you think about this, what this is telling me is a line with a slope of 2t with a DC offset. So in other words, what you could do is you could just solve for the Fourier transform of just the 2t line. And then if you add the minus 2, that's just a DC offset. So the only change that the DC offset is going to do is going to affect your A0 term, right? Your x of omega equals 0. So this would just basically subtract 2 from whatever the value is at x of omega equals 0. Because it's a DC offset. It only affects omega equals 0. Solid. Okay, let's talk about the easy way. So now it's just calculus nasty land here. Okay, and we're certainly not going to spend our time doing that. So how did I want you to do this problem? Take the derivative. Okay, so let's do that. So if we take the derivative, we've got to be a little bit careful. So this is x prime of t. So I'm starting at t equals negative infinity. So 0, 0, 0, slope is 0. Okay, now I get to negative 1. What happens at negative 1? Impulse. Talking about the impulse. Minus 4 units occurring at t equals negative 1. You see here this? You see this discontinuity? If you take the slope of that discontinuity, it's an impulse. How big of an impulse? Negative 4. Okay, because it's got to be big enough to get you down 4 units. So at t equals negative 1, I've got an impulse of area negative 4. Okay, great. Now what do I have? So now I got past t equals negative 1. Now I'm between negative 1 and 4. What's my slope now? It's a constant. And what's that constant equal to? 2, right? We already solved for the slope of that line. So now we look at the derivative of this line. It's the constant 2. And that goes on until we get to t equals 4. And then what happens at t equals 4? We get another negative impulse. Okay, and that impulse is going to have an area of negative 6. And there you go. So right now, I've plotted for you the derivative of x of t. Now, can we get the Fourier transform of the derivative of x of t by inspection? Yeah, let's do it real easy. Let's start with the impulses. So what's the Fourier transform of this impulse? Minus 4. Right? If it was an impulse that, remember, impulses at t equals 0 have a Fourier transform of whatever, just it's the constant, whatever the area is. So minus 4. But now I'm going to shift it to the left by 1 unit. So that makes it e to the minus j omega.
No, positive j omega.
Positive j omega.
Yes, I agree. Yeah.
Because if you go right, then you start a negative.
Yeah. Right. Remember, it's if you have x of t minus big T, and you take the Fourier transform of that. So this shifts. So this is x minus t. That's this. So you do a u substitution. U equals t minus big T. So that means you have the integral of x of u, e to the minus j omega, u plus big T du, which is the same as e to the minus j omega big T integral x of u, e to the minus j omega u du, and that's just x of, that's the Fourier transform of x of t. So that's just x of omega. Right, so if you put a minus t here, it's minus t here. So
It's a minus t.
so you did a plus 1, so there's your plus 1.
Okay.
Okay. Right, this impulse is minus 4 delta t plus 1. And therefore, because it's plus 1 here, it's plus 1 here. Okay, Let's do this impulse. What's that? What's the Fourier transform of that one?
Minus 6 e to the minus j omega.
Minus 4j omega. Okay. Good. And now we need the rectangle. What's the Fourier transform of that rectangle going to be? It's going to be a sinc function. Okay. So, plug and chug. Don't make it harder than it needs to be. Okay. So the first thing we need is little a, right? The half width of this thing. So what's the half width of this thing? Where's the middle of this thing? What's the total width? 5 units wide. So the half width, right? The half width is 2.5, right? Right. And then, well, hold on. So remember, the formula is sine of a omega over a omega times the total area, right? Okay. So I know my little a. Now I need to scale it by the total area of the rectangle, which is
10.
right. It's a width of 5 and a height of 2, so that's 10. So let's see. So I've got plus 10 sine 2.5 omega over 2.5 omega. And then there's one more thing I have to do to that rectangle. Shift. It's been shifted to the right, right? Because if I just do this, this assumes that the whole thing is centered at 0. But is this rectangle centered at 0? No, it is not. It's been shifted to the right by 1.5 units, right? It's not centered at, if it was centered at 0, it would go from minus 2.5 to 2.5. But it's not. It's been shifted 1.5 units to the right, so it's actually going from minus 1 to 4. So now I've got to take this and shift it 1.5 units to the right. How do I do that?
E to the minus j 1.5 omega.
Yep. There we go. So by inspection, no integrals required. That's the Fourier transform of the derivative. And now I wish to get the Fourier transform of my original function. Okay? So that would imply that in the time domain I'm going to integrate. So in the frequency space I'm going to have a nice day. Clean it up if you wanna. I don't care. Yeah.
So where's the impulse now?
Buried in there somewhere.
The impulse should be 2, right?
Well, no, it's 2 plus whatever you had from the 2t. For real. It's in there somewhere. It's hard to see because you've got a bunch of these terms like sine of 2.5 omega over 2.5 omega, which you have to resolve using L'Hopital's rule at omega equals 0. And you're actually going to wind up getting almost the same thing from this term with some... You could solve for it.
Yeah, because my question was, that should give you a sinc function, right?
This? No.
No, the left side, that doesn't? Yeah, that doesn't.
Well, this could be... No, this doesn't give you a sinc function.
That would give you a sinusoidal.
Yeah, you could. Yeah, that'll give you a cosine. Cosine or a sine, one or the other.
Yeah.
Yeah, basically what you could do, if you wanted to clean it up, you could take these two, factor out an e to the...
I just wanted to find the a sub 0 from there, and I couldn't.
Right, well you can't because you need, like I said, you need L'Hopital's rule to figure it out, I think. Because you've got a 0 in the denominator.
Okay.
So, yeah.
If the original function had a negative slope instead of a positive slope in the rectangle that we got from taking the derivative, the rectangle actually had, it was a line, it was like a negative rectangle.
Yeah, you just have a negative area.
You just have negative area, so
Yeah.
it's the signed area.
Yeah.
Okay.
Now, the cool thing is, I will say this. If you do the integral approach, and if you do this approach, you should be able to, if you massage the calculus long enough, you should be able to get the same answer at the very end.
Okay.
At the very least, to prove that they're equivalent. Because they are equivalent, because there's only one right answer. And it's probably worth doing it once, just to see if it works out. I mean, you'll burn what, like 20 minutes? It might be worth the exercise just to see if it works out. At the very least, you'll remember your calculus a little bit better. Yeah, it should work. Anyway, a great example of a problem where, now, if you're on a test, okay, a great example of a problem where there's an easy way and a hard way. I don't know if you could argue that this way isn't that much easier, but there's certainly no calculus involved. There's a lot more steps, but there's no calculus. So, I don't know, pick your poison.
You said you would take that as a final answer.
Totally. Yeah. And honestly, if you wrote this, I'd give you most of the points. I'd at least give you half the points. Right? Well, you know, I usually give John some advice about how to proceed, but I don't know. As long as he's consistent, it's okay. That's a good question. Thank you. Yes, sir.
Can we take another derivative and get a cosine function out of just the two positive parts, the negative 1 to 4?
Sorry, say again?
If we took the derivative again, we just have two sticks, two positive sticks. Forget the stuff under.
But then you'd be taking a derivative of an impulse. It gets ugly. Derivative of an impulse, not an impulse. Yeah. Well, I mean, in essence, but okay. What you could do, I'll give you this food for thought. Suppose you had completely forgotten about the relationship between the rectangle and the sinc function. So what you could do is this. You could say, okay, oh rats, I have to take the Fourier transform of this function. Okay? So you say, all right, well, I remember what the Fourier transform is of this impulse. And I remember what the Fourier transform is of this impulse. But I don't remember what to do with a rectangle. Crap. So then you say, okay, well, let me just redraw that rectangle. That rectangle is, let's see, goes from -1 to 4 with a height of 2. Okay. So you say, I'm going to take the derivative of this. Okay. What's the derivative of that going to be?
Should be a cosine.
You get one impulse here, and then one impulse here. Right? This impulse has area 2. This impulse has area -2. What's the Fourier transform of this function? 2e to the j omega minus 2e to the minus 4j omega. And then, if you want to integrate to get your square pulse back, you divide by j omega. I submit that this is the same as that.
We just add the impulses.
And then you add the two impulses in, and then you add the two impulses back in, and that's it. Is it true? Is it true that this equals that? It has to, right? I mean, both of them represent the Fourier transform of that rectangle. How could I show that it was the case?
Euler said that.
Screw Euler. I can't believe I just said that out loud. What I would do, you got a 2. Out of each term, I'm going to factor e to the minus 1.5 j omega. So what does that leave me with? E to the 2.5 j omega minus e to the minus j 2.5 omega all over j omega. What's that term? This is 2j sine 2.5 omega.
Do we need j omega squared? Non-arrow there.
Wait, no, right here I only integrated once just to get my rectangle back. Then I'm going to integrate again.
That'd be.
Yes. What's that?
That what the circle over there would go with the circle over there.
Yes.
So it's
Yeah.
j omega.
Right. Then you'd still need another. Right. Well, what I'm pointing out is that this j omega is going to disappear, into this. Right, and then you divide by j omega again to get your original function back. Let's see. This j cancels. So that's 2 times 2 is 4. Is it going to work out?
Yeah, it should.
Yeah, because see.
If you do 10 divided by 2.5, you get 4.
Yeah.
Yeah, right. Okay, exactly. So that's the same as 10. So it's, right, 10 sine 2.5 omega over 2.5 omega e to the minus j 1.5 omega. Works out. Pretty nice. So it doesn't matter how you do it, integral or shortcut method, you should get the same thing.
Question for
Fall 2010. Fall 2010. Were you guys even in college in fall 2010?
First year.
I feel old.
You're like the first professor I saw at Temple.
Sorry to hear that. and you stayed. All right, fall 2010, I'm looking at it.
problem 4.
These exams are so long. Consider the function x of t shown here. Suppose this function is filtered with a single pole low-pass filter with omega c equals 50 rads per second. As best as you can, sketch a reasonable approximation of what y and y... Oh, boy. Well, okay, so this is another example of a problem that we... Well, if you look at the date on this exam, it was November 22nd. So it's almost like 3 weeks out from where we are now. So this is material we haven't covered yet. Well, okay, but you could still give me a rough idea what that would look like with respect to time, right? I mean, you could sort of do this problem already. The only thing you would be a little bit suspect on is like some of the details of the numbers. But this is a rectangle, right? If you low-pass filter it, what's it going to look like? Yeah, if you low-pass filter it, where's the high-frequency portions of that rectangle? The corners, right? And the low-frequency portion is the flat parts. So if you low-pass filter it, you're going to lose the sharp edges, because that's the high frequencies that you're losing. All right, so here's your rectangle. If you low-pass filter it, you're going to pass the low parts, and you're going to reject the high parts. So we know that roughly what you're going to expect is going to be something that's going to look like... The only thing that makes a difference is the time constant, right? So here I've set a cutoff frequency of 50 rads per second. The only thing that would change if I change the cutoff frequency would be how quickly it rolls off. And actually, we've talked about that as well, haven't we? We did a demo on that. We didn't really get into a lot of specifics about how to calculate the cutoff frequency and like how that corner is affected and time constants and so on. But I mean, we've discussed it in broad terms. From a frequency perspective, what would happen? Past the low frequencies. What's the Fourier transform of this rectangle going to look like? Sinc function. And if I low-pass filter it, what's going to happen to that sinc function?
The first couple frequencies are going to bounce.
Right. I'm not rescaling in terms of like stretching or anything. I'm either going to, the low frequencies, I'm basically going to keep as is, and the high frequencies, instead of having these nice bumps here, they're just going to get mushed down to basically nothing. So it's not going to look a whole lot different. It's just that my higher frequencies are going to get reduced, while my lower frequencies are going to get maintained exactly. And again, all the cutoff frequency does is it decides how many of these bumps I essentially get to keep before I start really deleting them away. So I think beyond answering your question in more detail beyond that is probably a bit beyond the scope of this. But I mean, we're not too far off from being where we need to be. Yes, sir.
Are we supposed to use Bodie plot to plot that?
This is so the Bodie plot is basically just a fancy term for plotting the transfer function, right? And plotting the transfer function, and we've just like for a low pass filter, is basically, I mean, that's a Bodie plot.
Okay, so only for the transfer
essentially we've been drawing, we're just debating a term. Bodie plot is a transfer function, is like the Fourier transform of a system. You've got a system and you've got a signal. If you take the Fourier transform of a signal, we've been doing that all semester. If you take the Fourier transform of the system, you call it a Bodie plot. But it's this, I mean, mathematically, it's exactly the same thing. Which is kind of cool, right? Signals and systems are really the same thing. Right? If I give you a function, right, you could either think of it as an impulse response of a system and tell me that, look at the frequency response of your system, or you could say, oh, it's a signal. I mean, it's mathematically the same thing.
Probably filter, right?
Totally. Yes. We've got, a good 7 minutes, maybe 8 if I stretch it.
Will we be given, for fall 2008, they have a problem that gives you the transfer function, and you have to plot the Bodie plot, and then find the magnitude at J100. It's kind of like doing the log plots.
Yeah, we didn't. I don't think we really spent a lot of time on that for this time around. Yeah, I wouldn't sweat that too much. I wouldn't sweat that too much. Again, that was something that we spent a lot of time on that semester. You got to remember, every time I teach this is different. And partially that has to do with whatever baggage people bring from Circuits 1 and Circuits 2. Like sometimes people have had a really good experience in Circuits 2 for whatever reason, and there's a whole lot of material I don't need to touch. And other times, Circuits 2 maybe didn't go so well the prior semester, and we have to dredge up a lot of old material. So there's a lot of variability in these exams. Yes, sir.
I had a question. If you think about, like, let's say you have some kind of filter, right? And you find that is made up of a low pass filter multiplied by something else. Right?
Multiplied by something else. Okay.
Yeah, multiplied by, let's say, it's j omega, right?
Okay.
So since you're multiplying by either j omega or dividing by j omega, could you find what kind of filter it is? Like, pretty much, how would you find what kind of filter it is? Like, if you have some random transfer function, how do you find it? If it's a low pass or a high pass?
It's just do that as omega goes to infinity and as it goes to 0,
Yeah.
it's just determine what passes and what doesn't from that. I mean, that's
Yeah. I mean, if you think about it, a j omega filter, right, because if you're just multiplying by j omega, that means low frequencies are being multiplied by j omega, where omega is low, small. And when omega is big, that's a very big number. So that's, by default, j omega is a high-pass filter. And if you think about it, it makes sense, because j omega does what? Takes a derivative. Okay? So if I showed you this signal, and I said take its derivative, okay, you would have nothing, and then a big peak, and then nothing, and then a big peak. That's a high-pass filter, isn't it? Because you've only passed the high portions, and you've rejected the low portions. So a derivative is in essence, that j omega, that derivative, is in essence a high-pass filter. And integration is in essence a low-pass filter. Right? Dividing by j omega has the opposite effect.
So is this like those differentiation and integration op-amps?
Yeah, absolutely. A differentiator op-amp is basically a high-pass filter, and an integrator op-amp is basically a low-pass filter.
Do we got time for one more question?
If I talk fast, what you got?
Spring 2011.
Spring 2011. Number 2. Stand by. It's loading.
It's just a low-pace filter, but we got an extra capacitor with a resistor.
Consider the circuit show here. Solve for the transfer function and comment on whether it's high pass or low pass. Show all work. Okay. At low frequencies, what's that cap going to do? At low frequencies, caps are open. If that cap is open at low frequencies, what's y of t going to be?
Be 0.
Be 0. If that cap is open, there's no path to ground, so y of t just shorts to ground. So at low frequencies, y is 0. At high frequencies, what's the cap do? Shorts. If at high frequencies, when that cap shorts, what's going to happen to Y?
Going to be equal to R2 over R1 plus R2.
Right. At high frequencies, when the cap shorts, you're left with a voltage divider, R2 over R1 plus R2. So that's it's like a high pass, it's a crappy high pass filter. How about that? Right? So it's basically at low frequencies you're getting 0, and at high frequencies you're getting R2 over R1 plus R2. And at low frequencies you're getting 0. Okay? And if you actually did the phasor analysis or whatever, you could actually get the equation that describes this plot. But I'm just eyeballing this plot, and this has to be the plot just based on this eyeballing the circuit.
Now, when you do the body plot, do you get it to flatten now?
Yeah, it'll flatten. It should, right? I mean, the transfer function should be R2. It's a voltage divider, right? R2 over R2 plus R1 plus 1 over j omega c. Clean up the math a little bit. So hold on. Multiply numerator and denominator by j omega c. So that gives you j omega R2c over j omega R1 plus R2c plus 1. So how many zeros do you have? You have a 0 at omega equals 0, and you have a pole at omega equals minus 1 over R1 plus R2c. So this was, okay, so this here I've plotted this against, I guess, a linear axis. If you were to do it like a true Bode plot style, you'd have a 0 at omega equals 0, and then you'd have a pole at 1 over R1 plus R2c, and this value would be, we said at high frequencies, is when omega is big, you get R2 over R1. There we go, that's a better plot.
When do we actually start transmitting information with all these signals and systems and whatnot?
So when?
Yeah, like what course? Is that what control systems is about? Or?
Control systems is, yeah, I mean, you'll get some of this in control, some of this in communications. Is sort of like the applications of this stuff. Controls is less about communicating information and more about using this math to literally control systems. So controls is like, like let's say you've got a system, like an incubator that you want to keep its temperature at a certain temperature. Okay. So what happens is you send a control signal to set the thermostat, and then obviously if it's too hot, you want to turn the thermostat off, and if it's too cold, you want to turn the thermostat on. But heating, the thing that you're trying to heat has a time delay, right? It actually takes some time to heat up and some time to cool off. So there's this whole like delay element involved. It's almost like a filter. So now you can make these control systems that in essence say, I want to keep this thing at a set value, but I know that the system takes time to respond, and I know my system takes time to turn on and turn off. So when do I need to, how do I calculate when to turn the thermostat on and when to turn the thermostat off? And there's a whole bunch of math that goes into that, and it's all this stuff, and that's controls. But that's actually one of those vital things that engineers learn because, the thermostat thing is like a pretty rinky-dinky example, but if you think about most things, if you're controlling just about anything, which is what engineers do, like you're controlling a car, you're controlling a motor, you're controlling, power in a chip, you're controlling anything, it's all built on these control systems. So it's kind of like at the heart of what electrical engineers do. And this is all the math that underwrites all that. So we'll do some examples too where we actually transmit real signals, don't worry. We're getting there. Don't forget your homework assignment as well. I know it's sort of there in the back.